welcome to the machine learning seminar. Today's speaker is Pablo Montero Manso, and Pablo is senior lecturer at the University of Sydney, where he has been postdoc before, and before that he received a PhD from the University of Coruña in Spain, right? And if you check Pablo's work, there is a lot about time series data, not only forecasting, but also classification, time series clustering, and visualization, which is very interesting, not only for time series fans, I would say. Pablo is also involved in practical applications, for example, the WIRE project around energy consumption, but he has also been strongly involved during the COVID pandemics, especially with decision-making processes in Australia, but also in Spain and the European Union. I reached out to Pablo at some point because I had some specific questions about the Monash time series forecasting archive, and he was helping me a lot with this. And at some point I thought, why don't you give a talk here? And Pablo was just about on his way to Australia and thought about why not coming to Auckland for this talk, right? So we are happy to have you here. And Pablo is just coming from California, actually, right? Yes. So he's also visiting faculty researcher at Google. And today he will talk about large pre-trained models achieve near optimal time series forecasting. And I'm looking forward to this.
So thank you, Stefan, for the presentation. So I'm going to talk about large pre-trained models that achieve near optimal time series forecasting. So hopefully you will require a lot of clarification what you mean by near optimal, right? So these are very strong words, and then large, we'll see about large, that's more relative. I will not make jokes about large or small. And I am, I am a lecturer there at the University of Sydney, and I'm visiting the Google Cloud team that does the forecasting, but the cool thing is that they basically do the models for the forecasting all across the alphabet, basically. So this is a very, very cool team to be visiting on, and trying to work on some forecasting stuff. So the talk that I'm going to give you, I can summarize it, right? Trying to give you in a nutshell. The idea, right, if you want to get some out of it, is that what I'm suggesting to do is to train a neural network on a vast amount of simulated time series that actually are generated from some models, right? Some time series processes that are very popular in the forecasting space, but actually might not be the newest or the more sexy of the models. But these are the ones that are used in industry. So I'll try to devote a little bit of time of motivating why is this. And then what happens when we do this is that we try the model on new and same time series coming from the same processes. And what we observe is that this network actually outperforms what we will consider the classic models or the classic estimators for those. Like if in example of, let's say you have linear regression, and we have linear models for that under their optimal conditions, right? When the noise is Gaussian, IID, whatnot, they have some optimality properties. And what I'm saying is that you can outperform these models, right? So it might seem surprising, even though depending on the property that you want to outperform, it might not be so surprising. For example, we have the classic example is ridge regression or some form of regularization. You add it on top of a linear model, and you can show theoretically that if you can outperform just linear regression, even in the conditions, you will suffer others. And well, we will try to understand what's the mechanism of action behind that. So why, when we observe this phenomena, why or what is the network doing? And then explore a lot of implications of the results, so specific applications. How can we leverage this effect on that? And I want to acknowledge, like, even though we can think about this in the time series foundation model space, this is going to be a bit more focused on actual, like a more specific objective to show performance rather than averaging across data sets that most of those already come also from my previous work. So anyways, but many of these foundation models, just to motivate you, in case you disconnect your brain when you see statistical models or classic models from the 60s, it's time series forecasting, it's times FM, sorry, I make a typo. It's that times FM model, which is a foundation model for time series coming from Google. Forecast PFN is, I don't know if they consider themselves a foundation model, but it's basically purely on simulation. Chronos, which is one recent, I think is coming from Amazon. Foundation model for time series forecasting also use simulation. So that's kind of the idea here. And just to motivate why simulations, I'm going to motivate it in a way that, okay, we are already doing in some other fields, even though we might not call it like that. I guess the most popular one would be the one referring to computer vision, right? So we have, let's say that we have models when we want to impose some property in our model in computer vision. The typical one could be translation invariance. I don't care where the ears of the cat appear in the picture, as long as they are ears of a cat, then this is a picture of a cat, roughly speaking. But there are other properties that, and this, we can impose this with the convolution and the max pooling layers, etc. But some other properties are hard to impose in the architecture. One being rotation, right? So I would say if you know how to make a neural network that is rotational invariance in the architecture, you would be relatively famous, but I'm not super expert in that field. And then other like zooming, etc. We want that to not affect the model. So we simulate, right? We get our original picture and then we simulate. So this is the same idea in some form. And the metaphor that I like the most for this, what I'm presenting here, is kind of the AlphaGo AlphaZero, which learns from completely, especially AlphaZero, from scratch without, you simulate from a model, which is the actual model of the game, right? So the value moves in the game. And then very quickly you can learn to, well, outperform humans. In this case, would not be so very surprising in the forecasting space, but because we know that models cannot perform humans since many years ago in forecasting. But and then another example is in robotics, right? So they can train actual models using neural networks. They train the models in physical simulations. And I like this analogy also because they have this expression in robotics, which is, I think they call it the reality gap, which is, okay, your simulation is actually an idealization of reality. The better you can get that detailization, the better it will perform the model in reality. So there is work to do in that space. Yeah, so basically the message is that think about simulating from classic process as a form of super sophisticated data augmentation, that maybe the input is one integer, which is the seed, and then the output is a full data point in your model. And I'm going to try something a bit experimental, which I'm going to try to make an analogy for all of the ideas that are in here, but with a non-time series example, which is what I think is very evoking, very evocative, which is kind of the problem of disease prevalence estimation, which is, okay, you have a finite population, let's say it's a small population, you have a limited sample.
Slides don't progress on Zoom.
No. Where are you on Zoom?
We're on the title slide.
Okay.
Oh, interesting. So we are.
Maybe let's try to kind of stop and share again.
Yeah.
Okay.
It's not on the title slide for me. Maybe it's your computer, Jörg.
Oh, okay.
Okay. I'll let you.
Maybe we have several. Maybe I'm sharing.
Do you see the
Do you see the blue and the blue
people?
people with the orange one?
Yes.
Oh, okay, then yeah,
Okay.
continue. I'll talk to you. Just let him.
Yeah, but maybe, yeah, okay.
I will.
Anyway.
Okay, you can go on. I will make it a message in the chat that people can write me if they have similar
Because
problems.
maybe I might be, and I realized that I forgot about the funny anecdote. I'll make it at the end about where I come from. But so basically, this is just not to forget. The point is that this is an analogy with what I'm going to show in this is prevalence. Okay, we have a finite population, we have a small sample, and we want to guess from this small sample how many people are infected in the total population. And in this case, we kind of know, even though epidemiologists might debate it, that there is a governing probability distribution that the same as the Bernoulli can govern throwing a coin. This experiment has a probability distribution that is known. It's a famous probability distribution, the upper geometric distribution. But for example, just to derive, right, so just to arrive at this formula here, there is some technical difficulty. If you ask me, derive the hypergeometric distribution from scratch, right, in a universe where this was not invented, I will be hard pressed. Don't tell that to my professors in my PhD program. So this I want to say with this that there is a technical complication here, right? So the finite samples make it hard. In time series would be the serial correlation, right? So statistically speaking, and we actually have.
Once I was with you. Thanks for giving us a heart attack midway through.
Yeah, you are not muted.
Okay, so yeah, and then we have to solve this estimation problem is actually, well, you could argue whether it is an open problem or not, but several algorithms have been proposed. One, you might be familiar with the approach of maximum likelihood. Do we have the Bayesian or the Bayesian posterior mean, even though if people are Bayesian, might disagree with this, so just making it, let it be known. And then we have this kind of idea, which is the minimum variance and bias estimators, right? So which is your estimator, right? So the algorithm that goes from the data to whatever it's going to predict, in this case, it's the number of people infected, has to be unbiased. And this is going to, that's why I like this example, because it's going to analogy and let's say, like friendly speaking, is going to kill a lot of the papers that have been published here. And these are the algorithms, right? So the maximum likelihood is doing this flooding of the, I think is the total population size, which you know, times what you get out of the experiment divided by the sample size of the experiment, right? So in this case, I'm just giving you an example, right? So this is going to be meaningful in a few slides, but imagine that in this case, you have a population of 200, we sample 5 persons, and we get 0 cases. Maximum likelihood will give you 0 people infected. A Bayesian with a uniform prior, and this is where people can disagree, but it will give you 25, which can be, if you think about this problem, the difference between no infected people and 25, like I guess it's 12% of the population is quite, and then you will have the minimum variance and bias estimator. And why is this an analogy? Because, well, for example, via simulations, anybody, even though if you are not familiar with even with the concept of randomness, statistics, and probability, you can simulate from this problem, because we can basically, up to some size of the population, we can enumerate all possible cases, right? So you don't need to do any randomness. You can enumerate them and just quote simulate, right? And the idea here is that we can enumerate all possible cases that we can come out of this experiment and then pre-train a model just to map end to end. This is my sample, even with the order of people that we are sampling. What not given enough data, it will be able to pick one-to-one perfectly without, well, just the gap in the gradient descent when it converges. You can pre-train this model to, well, whatever you give me that comes from these possible situations, I know what's the perfect answer, right? So this is, you are learning into basically a retrieval, right? So you just memorize all possible cases. In this case, it's perfect because this is what's going on behind, right? And then the benefit is that especially in the deep learning space, we can actually choose which optimality criteria we want. For example, instead of a square error, you can change the loss function to maximum average error, square error, or many other properties. Ones might be more difficult to impose than others, but as long as you have a gradient, we were optimistic and we think that since we have infinite data, it will work. So that's the analogy, right? So in some form. So the idea that there is something process going on that we can solve, well, maybe just to keep the attention back, right? So we have a kind of hard problem that we don't imagine that we don't know this governed distribution, but we don't care because the network we're going to learn, in this case, you can learn this problem in 5 minutes in maybe a Google Tensor processing unit. And via pre-training, and then you can also, once you have that, you can even go beyond and impose properties for which we don't have this nice closed form solution. And now what I'm going to do is motivate, let's see how I'm doing with time, the time series part, and what models are coming out of this time series space. So depending on how familiar you are, this is going to be very familiar, but we all love exponential smoothing. No, it's not my favorite model, but I might say that it has won my heart many times over. So the idea of exponential smoothing is actually, roughly speaking, it's a very simple and beautiful. It has many connections with physics, etc. But imagine that we have like a composition of 3 underlying random walks. So assuming that you know what a random walk is, you have a random walk for what we call the level of the underlying state of the time series. Then the linear, we have a linear trend, right? So that how it grows with time, that it's also a random walk itself. So the trend, the parameter of the trend has a random walk noise component. And then we have a periodic pattern that it's also affected by a random walk. So you can think of, we call it a 3-parameter model, but it actually has many more than 3 parameters because we have to also consider the starting hidden state, right? And it's actually, for example, this idea of exponential smoothing is very popular in industry, as I'm going to motivate later. But even in the deep learning space, the models that started outperforming, let's say, the classic statistical algorithm had a component of exponential smoothing structure embedded on top of it, either as an encoder and now maybe as a decoder, meaning that, for example, you can, well, broadly speaking, you can run exponential smoothing, fit it, and then whatever is exponential smoothing is not picking, try to pick it with a neural network, or impose in the head of your neural network that's going to predict, impose that the shape of the predictions, instead of being a free form, whatever fits the data, you just restrict to being the valid shapes of exponential smoothing problem. And for the people that work in other fields of machine learning or deep learning, there is a difference here that I would like to highlight, is that in forecasting, the shape of, or the flexibility of the function that has the predictive function is actually not the problem here. It's not the difficulty. For example, in computer vision, we know that if there is no linear function that predicts cuts from a picture. We need to transform and add some nonlinearity in natural language process. I thought, who knows if there is if you can turn the problem into a linear prediction problem, but that's the case, right? So we know that we have some complexity that is way higher than just a linear pattern from the input data. And just to show, I have a little game here prepared, which is, can you guess which ones are synthetic? These are time series that are real data, which are synthetically simulated by exponential smoothing and which are not. These have been, of course, cherry-picked, but the point here is that these are all full data. The one that is your training data, what you want to predict, right? So the point here is that nature, well, let's say it mimics nature relatively close, right? This is half and half, so half are true data points and the other half are not. And for example, you could say, I would say it's the easiest one, that this is synthetic, right? It looks too regular, but it might also happen in some practice, right? So, but there are others. This might be also too regular in my view, but I think this is real. So I have the cheat sheet. I don't have it right now because I'm full screen, but just in case.
It's like a Bitcoin, right?
Yeah. So yeah, so but this is the point. These are quarterly time series. So these are series that we have 4 data points per year. But that's the point of the motivation, that when you have this input data, there is no much need for that, right? The business part that maybe is the less well known, so of exponential smoothing, is that not only that you might not need that much flexibility, also that if you give the decision maker some forecast that is not linear, might be also, what do I do with this? Like, even, for example, you plug the forecast into a linear program, like a linear programming or optimization algorithm to make an optimal decision out of it. You might get problems with that. And then the coefficients that govern exponential smoothing, the three coefficients, the alpha, the beta, and the gamma, are actually meaningful. A lot of people are trained in interpreting them. Basically, these coefficients go from 0 to 1. 0 would mean that white noise, and 1 would mean a random walk. So it's like kind of the sliding tuning parameter there. So it kind of, the interpretation is kind of the reactiveness of the process. You can look at a time series and, okay, does it react? It's very impacted for recent changes or not, right? On people, for example, in the sales industry, the ones that work with data, care about those things. Like, is my product reactive to whatever goes in the market or not? All of these, or previous sales or not. And then another, the flip, is that sometimes you actually know something, like the expert knows something that can introduce via these parameters. They can express, I know that my time series, it cannot be very reactive in the linear trend, for example. And you add that, so, and they want to have this control, even though you might disagree from a pure data science perspective, but this is something that happens. And then when things go wrong, right, you get a forecast that is really not well or sounds very suspicious. What do we do with it? Do we trust the model? Would you trust your whatever $1 million decision in transformer, etc.? Or do you look at the parameters, etc., and you know whether this is crazy or is actually something going there? And also sometimes, and an interesting point is that you don't need the, as long as you get the alpha, beta, and gamma, you don't care that they come from, well, I guess you would care, but if they come from neural network, you are still the same. You can still interpret the same. So, and also, finally, it's an area that is still improving. People are improving of the ways. How can we get the line? How can we fit a line in time series? Is still an open field of research. And finally, the interesting part is that it's basically billions of, or I don't know, even trillions of dollars every year of decisions are informed by exponential smoothing forecasts. Right? So this is the $1 million.
Yeah, the $1 billion. Yeah.
And then, so some of the insights that come out of here will apply to other models. And finally, if you want to make the joke that exponential smoothing, if I would sell it today to get some grants, I would say that it's like a special recurrent neural network with some properties, but it actually is because it's a recurrent model. You can pose it like that, and you can put some like special transfer functions in at the head, etc. It kind of, you can also make the case. I can also make it as an attention. So if you understand the model, you can make all this case. So what we are going to show is results on, okay, hopefully I have motivated exponential smoothing, and now I'm going to pre-train on simulations of exponential smoothing and compare it to the actual exponential smoothing, the estimators that don't know the actual true parameters, they have to get them from data. And I'm going to put some scaling laws. I'll post the quote because there is no scaling law with the number of parameters, even though I have some results, but not serious. But it's the scaling laws with the data and maybe some other things that are relatively newer in the sense that since we know what is generated in the time series, we can get some scaling law depending according to the parameters of the models. We simulate uniformly, right? This is between 0 and 1, because these parameters are nicely between 0 and 1. And length of the time series is between 15 and 64. You might be disappointed in the 64 data points within I have experiments with many more, but this is just to understand, and I want to iterate quickly over experiments. So then there is Gaussian noise, and the starting states also are random, and seasonality is either 1 or 4. And the benchmark is what I call a super paranoid benchmark, because when we start getting these results of performing classic models, you get very scared that your old professor are going to hate you forever, or etc., or humiliate you if what you say you are wrong. So what I did is I compared to several exponential smoothing implementations, not mine, and then they know all of this, right? So they know that it can be 1 or 4. They know how the random starting states are chosen, right? So the range of the parameters, etc. And finally, the data that I simulate in the test set is actually it's not my implementation, right? Because I have an implementation that is super fast to train the neural networks faster, but which I check that it's the same, but I'm using a different, different random number generation, etc. And the architecture, we are going to start with a smaller big model, but it's a 1 million parameter dense-net architecture. And what I chose this one is because the linearity is kind of important in time series. You can, so the dense-net is going to pass the input to the output to the final layer. So it's going to be, the interpretation is a linear model with some nonlinear variables added on top of it. And I'm not the first to do this. So there are some time series models that have the same idea embedded. And then it's a causal CNN, but it's kind of a joke, but it's actually, yes, a causal CNN with no dilation, no time dilation. I'm not sure if you're familiar, but the time dilation is you put whatever the receptive field jumps very far away into the past. So it's not, and the idea why I don't do the time dilation is because we want basically to be discovered by the data. So this is actually, you can make a case that time dilation can be the seasonality. The cyclical pattern that happens, once every 12 months is a yearly pattern. So you want kind of that to put it with more importance in the network. That's why you put a time dilation, and then the transfer function is a leaky value. And this is not a super strong statement, but what I found is that we will see in the training, but sometimes it can get very crazy. It kind of kills the learning rate of the network, because I don't know, it might kill the values, etc. But this is not a strong statement. Focus, basically, I want the model to be trainable, right? I want to converge because I have infinite data, so it solves a lot of problems. And I also want to iterate fast through different experiments and to see that everything goes well. And basically, this is the size of the training set, right? So I am simulating from many time series. If we normalize to time points, so basically, if a time series have length 15, it will be 15 time points. The size of the training set that I'm showing here is 4 trillion. And just to compare, other foundation models trained at this scale. This is going to be kind of, even though it's being recorded, but this is kind of also, I don't know, like an attack or whatever to other foundation models when they claim performance, because we'll see that the amount of data that we need even to approach the performance of these classic models. So what we have here, I guess it's the first, I don't know, scaling law, even though, which is the performance in prediction error on the test set, a new unseen time series of this model as when it's training, that I realized too late that I could already put the size instead of epochs. But basically, each epoch, I put it at 20 billion data points or time points, just to show some progress and do some checkpointing in the training. And we observed several things. First, that it ends up outperforming the classic model, right? Which is in orange. So the classic model will be exponentially smooth trained by least squares, or the maximum likelihood estimator. And then what we'll see is that, well, eventually at about 30 or 40 iterations, so I guess close to 1 trillion might be in the next, is when we start outperforming the classic model. So this is a lot of data. Simulations is way larger than other. Already this, so I mean, already when I'm starting the plot, because I didn't put the first iterations, even though they look very, very noisy. You see these jumps here, but we already start at about twice the size of a foundation model. Right? So, and one thing that is that I like to highlight is also the training instability that happens. It was a book that I don't know. It took me a few days to find out. Is that sometimes when you simulate these time series processes, the process can really explode. Even if you do min-max scaling of the input data, not of the output will explode. Will get into millions of, right, because of the. If you add that the trend can change with some noise level over time, it's like you can get into some weird exponential growth, and in a few iterations it exploded, and you get some training problems or none the day you want to see how they train. So that's one example of a scaling law. And then the one that could be a little new, I don't know if you are familiar, you can tell me, you have seen similar things, is what I call is the information per series, right? So this time series each time series comes from a model. The longer we observe the time series, the more information we have, right? It's not like it's changing, the model underlying is changing over time, etc. So we can say that the longer the time series, the more information that we have about it. So I want to show what's the relative ratio between the classic model that is estimating the data versus this pre-trained model. And what we'll see is that, well, on average, on the left-hand side is what I call the tournament score, which is how many times is the pre-trained model better than the classic models, which is a very important metric because you can hide a lot of things in the average error. But so this is important, but we will see basically the qualitatively is that the benefits from the pre-training, or let's say it gets harder and harder to beat the classic model, the longer the time series. This is, of course, not very surprising, but you know, like when people claim outperformance and even ignore this fact. And on the right-hand side, we'll see the absolute errors, just for comparison. And of course, I can craft situation, that's the thing, where the pre-trained model was uniformly worse than the classic model, right? So this is as sure as linear algebra exists, right? So you have something that is very, very clean with not much noise, etc. The estimator that does least squares is like claiming that you can sum better than a calculator, basically. It's a crazy thing to say. And we can use kind of this scaling law. This starts with the not adversarial, but we are getting there into the, well, these scaling laws, maybe people don't call it that, but let's assume that to keep me happy, we'll call it scaling laws. It's basically what I'm showing here is the tournament score and how many iterations, right? So how does it evolve? And what we'll see is, for example, that if we compare to the classic model, depending on the length, we outperform or target, right, or enemy, we outperform it at a different number of iterations. So what this means, we can exploit this fact to simulate unevenly, right? I will simulate more for longer time, more times. I will more proportion in longer time series because I want to uniformly outperform my benchmark faster, or because it's more difficult, the problem gets more difficult with that, right? So this, we can leverage this idea to improve the sampling for the training. And it kind of gets nice because we actually have, when you look at the scaling laws, I think that they have a difficulty because you don't know to what you are going to converge. So getting a nice scaling law is not possible. If in this simulation scenario, we kind of can work out what's the optimal error that you can attain, possibly. So it's like you can, in the regression, you can remove one of the parameters that you have to, and this is the harder actually to extrapolate. So anyway, and you could get better scaling laws to get better, smarter sampling for your training. And also, well, that to outperform, right? So outperform length at length 64 to outperform the classic model, I needed 40-something iterations, which about 1 trillion data. So that's a lot of data. So in the training, but this is of course assuming that I'm uniformly sampling. Okay? So that's the point. I need 1 trillion data points to beat exponential smoothing for series of length 64. Try to convince a practitioner that 100 billion data points foundation model will do better than exponential smoothing in your application. That's the thing that what people, I kind of defensive against these ideas, because everybody in the, let's say in the industry has this intuition of, well, on average, on this data set that they do nothing like my data, you can do well, but how do you do here? So this is, right, so this presentation, what I'm trying to do is stronger guarantees of performance when you compare to classic models, and then how it can work also well in real data. And in fact, the longer the time series, the worse it becomes. Of course, the counter argument for that is that actually, since exponential smoothing is not a perfect modeling of reality, we can outperform it because reality is not an exponential. Well, basically, that's the circular argument with all nonlinear models will give you that, right? So it gives you, well, since reality is nonlinear, my nonlinear model should be better. So that's the, but it's like a lazy argument. But it can be true, but so far it's not much evidence for that. And there is another interesting thing is that the pre-trained model has actual access to the prior that used for the simulation, right? So it knows the range specifically of the parameters. It in exponential smoothing is not so important, but in other models where we cannot actually sample the full parameter space, imagine a linear model, you can say, well, how do you sample the coefficients for your linear model to pre-train, like from 0 to, or from negative minus 50 to plus 50? What if in my regression problem, I need another number, right? So that's the idea, that you can argue with that, but we'll see how it becomes important later. And yes, you can argue also that my architecture is not the newest, freshest one, so maybe that's the reason, but I would say that, yeah, maybe you can improve 10% or whatnot, or 20%, but still it's going to happen, that problem. Then the final, which is not as calling law, but is comparing the pre-trained in blue versus the classic model estimator in orange versus the parameter alpha in the exponential smoothing. So this would be, if we go to the zeros, this would be white noise. So just, estimate the mean of something, right? The sample mean will be the optimal estimator. If you go to here, it would be full random walk, where the optimal estimator would be just predict the last observation. So these are the two extremes, and in between you'll have this, that the optimal thing will be to weight the more recent observations more important. So this is the error. So what happens is that, yes, the closer you get to a random walk, the worse the error becomes, because the errors are correlated, and this is super hard thing. If you know it, I guess it's the same, but if you know that you are in a random walk situation, you can do better. But when you don't know, right, the random walks, there is a joke, I think, in statistics versus finance, that you give finance people random walks and they will find cyclical business cycles, but I don't know how, because the finance people that I've met are very knowledgeable, believe me, of these random walks. But because this is the error, and the slash, the dotted lines are actually the bias. So I'm showing here already the bias variance decomposition of the error that is going to be important later. In this case, this is not very meaningful because it's like 2% of the error is, or 3 is the bias, and then there is the irreducible error, and then there is the variance component. But it's kind of showing that we can do this, go deeper into we don't need to just do average error. And so that could be the comparisons. And I guess the story here is that, well, we actually kind of proven that we can outperform. We need a lot of data, etc. And we even have all these metrics, like the tournament metric is not as nice as the average error, because it can get, it's more, I have a typo here. But now what I'm going to do is, well, with this idea, how can we exploit this idea to get better actual forecast in reality? So I'm going to start with, I would say, more like the contribution here, which be we realize that these pre-trained models act kind of like estimators, right? So it's not like I am fighting whether this is linear or non-linear. I am fighting whether you use least squares, maximum likelihood when they are different, or any other fancy estimators. But that's in my view, the thing that these pre-trained models are learning. They are learning the algorithm that goes from data to the underlying parameters, and then you don't even need to estimate the parameters. You can also do the forecast, but it's kind of the things that they are doing. And you are going to see quickly why this is very cool and is very important. And then we are going to try to do some robustness in the sense of typical problems in time series are outliers and missing data. So how we can leverage this simulation stuff to solve the outliers problem and missing data problem. And then other nasty things that can happen in time series, which are the change point or structural breaks, where the example that I use is price of NVIDIA GPUs before and after Bitcoin. Well, Bitcoin mining, yes, I think was a thing. So you'll see that there is something crazy after that. And then we are going to do model combination, which is other classes of models. We combine them, so we are increasing the flexibility, right? If you don't like exponential smoothing because it's so simple, we can combine them using the same approach. And finally, composition. So the pre-trained models as estimators is basically that we can look at what the statisticians did, what they asked for the estimators, right? And the interesting part here is that what we are doing in the simulation is kind of trying to, and actually I don't need to tell you that, there is another papers in the foundation model that they tell you this. These pre-trained models are doing the Bayesian posterior, right? So you simulate, when you train on simulations, you are simulating from the prior, and then you get the data and you get the posterior distribution for the parameters, for the predictions, etc. And this can be criticized, I guess not if you are more Bayesian, but you can criticize, oh, how do you choose the prior? And then, but it can also be dangerous in some cases, which also Bayesians might disagree with that. But we have some, right? So in the theory of estimators, we have some properties, which is what we call the minimum bias and bias estimator, is condition that your estimator has no bias. So if you give them a lot of data, will not make a mistake. Broadly speaking, might get retroactively have to go back to studying stats, but that's the idea, kind of, right? So you condition your estimator, so you restrict your estimator that it cannot have bias, so it cannot have systematic errors in any direction when you have on average, and then try to minimize the variance. And then there is nothing else. So that's why it's cool, because you can decompose the square error into bias variance. You have zero bias, then, and the minimum bias is like, well, this is the optimality that I talked before, right? So this is an optimality definition that might work for you or not, but this is the one that we are. And examples, of course, the one that I highlight here is the sample variance. And this is the joke that, you know, the sample variance, you have to divide the variance formula by n-1, right? But this is something that gets, well, I don't know. You use NumPy or the Python implementations, and they don't do the sample variance. They do just the variance formula. In statistical software, usually by default, when you get data and you want to estimate the variance, you get the sample variance estimator. But anyway, I'm sure that there are arguments for both sides, but this is just as a kind of slight joke here. But and now this, and what I try to motivate is why an unbiased estimator might be useful, and we come back to the disease prevalence estimate problem, right? So what I have here is a plot where in the x-axis is the true number of infected people in your population of 200, and on the y-axis is the average prediction. And the blue line is kind of the Bayesian posterior, and the orange one is once we have endowed or pre-trained model with this property of unbiasedness, right? So what you get is unbiasedness is, well, you get, on average, you get the perfect prediction. Well, yes, the underlying true minus some noise that can even be because of the simulation that I did. And I use this green dot, I continue, right? The green dot will be the real, the true, the optimal thing to say, which is that it goes further and further. Why do I mention this? Because this blue line will change depending on your size of the population. It can get really bad at the zero level, right? So, and if you think in decision-making space, yes. So if you have 25, 100 cases, when you sample zero, this, first of all, it's a very hard sell to the politician that has to stake their career on closing or not closing the economy. But you know where I'm coming from, right? So this is the potential exponentially growing implications of your decision that might be, you know, if you have, I don't know, hopefully not politically incorrect, but in a life-death situation, a gun to your head, which estimator would you trust? The unbiased estimator or the one that comes from a Bayesian prior that somebody that you don't know picked, telling you that is very good. So that's kind of the idea. It might, you know, might be a counter argument for this, but this is kind of one of the. I want to also highlight my own, you know, ideas. So, and then we can go beyond the minimum variance and bias estimator. We can look at all of the crazy clever mathematicians do in that space and try to copy them, or even impose some of our own. Like, for example, this is not new, but the minimum variance and bias estimator is using the square error sense. We can use the absolute error sense or whatever metric that you want. We can try to do that for example, for probabilistic predictions. And then you can do things like, okay, assuming that I give you this budget of bias that you can have, now give me the optimal prediction error. So that's the cool thing. And this is when I kind of get into the adversarial space, because to simulate, to generate these estimators, what you would do in my naive way of imagining an adversarial is that, well, this is the process. You can try to mess with my estimator, but you have this budget of deviation that you can get out of the true model, right? So you can change one data point up to this size, up to this norm of change. All of these things to impose properties or guarantees in the estimator that is going to come out of it. Another point that is super important in time series is the outliers. And what I have here is in a paper that the example of the logic that goes to solving outliers, right? So it's quite complicated. So an approach that I am kind of suggesting here, which is not my idea, but like the idea is that instead of sampling from the Gaussian distribution, you can sample from distributions that have fatter tails, so they'll have more chance to give you crazy numbers. And this is when you plug the student T in your simulations, is when you kind of start getting the nonce in your training, because it can produce 0, 0, 0, 0, 0, a million zeros, but kind of exaggerating, depending on the degrees of freedom that you put into your simulation. And yes, so there's a crude number that I'm not showing you here some super cool results yet, but can improve by a small percent. Also, the Foundation model LAG-YAMA uses the T student as the probability distribution head, right? So that's, but here is not the same, is that I'm using to prepare my estimator against outliers. And this is doubly cool because actually we don't know, well, last time I checked, but I might be wrong. But if I give you something like, okay, give me the mean of this population from a sample of independent, all nice, but I don't give you that I know that follows the student T, I don't know the degrees of freedom. We don't have a good solution for that problem. Even that simple problem, you have approximations of that because you have to guess the degrees of freedom, then use the mean, and just to give you like the sample mean, in the student T will be weighting the observations, the farther they are for, it's like gets crazy complicated. But here with simulation, we can, in one go, with a lot of data, we can solve that. And triply cool is that the students, which is Gosley, I think is the name, the job description was head experimental brewer. So he would work for Guinness. And then, so that's, and this is one of the problems. We'll see that it has ramifications, but kind of, you can make your time very robust against outliers by kind of playing with these distributions. And then you will see some foundation models, if you want to look what they do with the outliers, like these pre-processing steps or whatnot. The other is missing data. You expect 10 to 20% in reality of missing data. It's even harder in time series, right? Because even if you could make the argument that time series forecasting is actually a missing data problem, where the missing data is always at the end of the vector. And it's actually, but this is a joke, but the thing is that depending on the missing data appears, they have different ways to solving it, etc. And actually, what the standard, let's say, is to impute the data as a pre-processing step that is suboptimal, because it's just an heuristic usually, does not consider the model. Even so, some models actually do the optimal imputation. For example, some Bayesian approaches can do that. But for example, I can give you 2 foundation models that actually push that problem to the user, right? So you want to pay for that, but if you want to, you have missing data, you have to impute it, and then you give us the data. So I would say it's trivial to, right? So now, if I ask anybody here, okay, so how would you train a model that can have missing data? Well, I just put some weird masking values on the time series that I'm simulating, and then I would expect to get, and actually, yes, this is what happened, even though let's say that I had to make the model bigger, etc., and train longer than expected just by adding missing data. But that actually might be solved by a better architecture, right? Because the dense nets are very smooth. So if you put masking value, which let's say is -1, when the time series are normalized to 0, 1, it might not be the optimal thing to do, but anyway. And actually, I was surprised to find that these foundation models, they don't support missing data, but I thought that transformers for free will give you this property, but apparently they don't. I'm running out of time. Well, finally we have the change point where in many time series you have a change in the process that is very noticeable, and in the simulations, might be disappointing, but I thought that was very cool, which is that I'm highlighting here this is actually a simulated time series. It looks like it was a structural break, right? So it was going up, maybe, they hired me, and then they went. So this is not official financial advice. So it looks like there is a change point, right? But actually what's going on here is that the time series, the model itself actually allows for that. What we have here is a shock in the hidden state of the exponential smoothing model. So just as a simple exponential, something as simple and beautiful exponential smoothing can produce this kind of things. This is a completely quote-unquote regular exponential smoothing process. This has not changed. What has changed abruptly is the hidden state. Right? So one of the hidden states, which is the one that I guess controls the trend. So you get if you have a good model, you can be very robust against this kind of change points. There might be others that you are not robust against, but this is kind of the thing that you get. So that's another of the problems that you can solve here. And finally, the model combination. And I will assume that you are not so focused on model combination, forecast model combination. You, of course, know about ensembling. That is like magic, the closest thing to magic that we have in statistical learning or machine learning. You start combining models, and you get better performance out of sample. This result holds in time series, but it has papers go up to the 60s, like Engels, Nobel Prize in economics, talked about this. But there is a thing in time series, which is that equal weights in the model combination is very difficult to beat. And it becomes really, at least my monkey brain, difficult to understand that if every day you look at one model and it's better than the other, that you cannot actually say that I want to weight more this model than the other. It happened all the time. For example, in COVID, my involvement with COVID was because I had some good results in model combination, right? So one of these machine learning competitions that we got, I guess, second position. First, it would just average rank, but average error, second position. We did model combination and we observed the same effect, right? So in the US also, they use the same approach, and the European, right? They open, people, please give us your forecast, even though it might not be very good. When we put them in the ensemble, they will do their magic. Of course, in reality, if you have very, very bad models, right? So if you take the adversarial approach, you can really mess up a model combination. But if models are good, then more or less good, even though one might be systematically worse than the other, actually, it's very difficult to find out. So my approach, when I throw my hat to the ring to solving this problem is, okay, so let's pick a few models, and then we will simulate from these models plus all the possible combinations, the weights, right? And then generate time series with that. And this, what we get out of this pre-training is an estimator that is kind of optimal in the sense that I've been showing in predicting these model combinations. And this is like, well, I stake my career on this result. So I'm going to present in a few weeks, and I'm going to focus a lot more on this slide. But so that's kind of the idea. This is a powerful result. So I'm claiming that this can solve open problems for decades. And so that would be kind of the pieces that we can combine towards a foundation model. All of these ideas plus, of course, real data. But I don't need to be telling you that real data will help in the training. But it's kind of the idea of the properties that we can impose, and all the ideas that are flying around in time series, we can leverage them to improve performance. And then finally, just a few results that might be disappointing, but what I would do if I'm going to approach kind of foundationist model, even though I don't want to call it this foundation, is okay, you get exponential multi simulations. Another model, the ARIMA class, which we don't have time to cover. I'm running out of time. So model combination, blah, blah, blah. And then you combine them and you get better performance with this than the winner of the M4 competition, which was, a very impactful result and is applied in industry, etc. These models, which this is a neural network with some fancy architecture, etc. And what I'm telling you is just so far, exponential smoothing arima, which are linear models, plus combination, plus some data, plus some randomness, which is coming from a student C, and you can outperform them. A negative result is that, for example, when you look at papers that they simulate and they claim that they work so well, I can tell you that if you combine, for example, two model classes, you will get a no freelance result. Basically, yeah, a single model that knows about the class will outperform you. And you can use that argument instead of the model. You can use the specific range of parameters, etc. So that's why you can get a counterexample for whatever claim of performance that is too general, right? And then the nice thing is that, well, if the time series grow longer and longer, you can actually get away with more and more combinations of models and diversity in your simulation space. So yeah, that could be a path for a foundation model, but that's kind of the idea that I want to show some negative results. This is not magic. We are just trying to mimic some optimal performance for estimators that we are not able to do with closed form mathematicians cannot do it. We can do it with approximate with simulations. And so things that I cannot show here, or not, maybe, I don't know if they don't allow me to show it, but I'm not so ready, but I put a lot of time in accelerating the simulation, right? So I'm moving it to the tensor machines and whatever. And I try to accelerate it so much because if you look at the scaling laws, what they tell you is that, well, of course, the scaling law, so we'll give a trade-off between size of the parameters, data, etc. So I feel that it's good to have simulations that are super fast and you can generate trillions in. I cannot tell you how long it takes, but kind of that's the idea. I put a lot of time. I'm exploiting mathematical properties of the model to speed up the simulations, all of this stuff. And another one that I think is very cool is the mixture of expert. I don't know if you are familiar with this, but the idea is that I can have many models and they switch between them and basically and make the compute much faster, right? So compared to just adding the number of parameters. So you can get to trillions of parameters. And I think in this space can work pretty well. I am trying it, not the full implementation of that, but you can get like 10 times the models with what I'm doing, 10 times the parameters, and not 10 times the compute, let's say. And then other things that are implemented right now is super long horizon forecasting. It kind of became a thing recently. So we can simulate, right? In simulations, you can get very long future number of observations in the future. And then, of course, everything you can make it probabilistic in the sense of instead of producing a point, you produce the full probability distribution, and even not even like the marginal is like for every like the path probability, not the marginal probability, which is some people might be interested in that. So this is all the things that you can do relatively easily. Probabilistic is also nice because the more they go into the extreme quantiles, the amount of data that you need is more and more, especially of real data. It gets very difficult to estimate the quantile of something with whatever observation that you have in your data. So this is what, right? And finally, so I propose that this idea can be leveraged in two regimes. One is the general, which is the magic regime that I call, which is, well, let's pre-train on many things and then assume that data is going to solve our problems, and this is going to be what everybody's going to be using in the future. Or the one that is less ambitious, but it's also cool, is okay, if you know a little bit about your problem, you might be able to simulate some scenarios for that, and then you run it overnight, and you will get like an estimator that is tailored to your specific problem, right? So this kind of also, you want like the Bayesian approach of getting some nice priors, but it can get crazy. For example, you can get an agent-based models, like somebody is telling you, how can I predict the sales of, I don't know, shampoo in my supermarket? And then, well, I have this number of families, the number of, the shampoo you combine these, you put, and then you simulate from that, which is very difficult to get a mathematical model and then solve it optimally, right? So you simulate for that, imposing a lot of background knowledge. And I guess that's it, just concluding. I'm excited about this because you can bring people with different expertise. For example, just speeding up any part of the process will net inaccuracy improvements. you can also work just in the architecture. And one of the things is that with this simulation, you can benchmark your architecture better. And then you can try to model new processes that people didn't care about modeling them because it's going to be so difficult to estimate that, or work out an estimator that already of subconscious telling you, no, do not work on that problem. It's too hard and you will not get publications and you will get fired. So kind of the idea is that, for example, multivariate forecasting is one of those. People can work on mathematical definitions of possible multivariate problems that are super hard to get the estimator. And I highlight here the adversarial approach humbly because I don't know much about it. But the idea is, well, we can accelerate convergence of these models by exploiting another type of, sorry about that, the parameter space. Like, well, you can try to find out or generate time series for cleverly find out with a model where is my pre-trained model weaker or the model that I want to pre-train. Or the other ones is that, well, you can actually try to impose some optimality or guarantees based on adversarial approaches. So I try to mess with my model in some sense with an adversarial network that has some restrictions on. And then also I think that it can help, but that's having a model that you cannot deviate much from it can help with this mode collapse thing, etc. But that I'm not sure. And well, that would be the talk. Then it's just, I guess, that's the clever things of, well, if we have infinite data, it solves a lot of problems, right? So the architecture might not be so important, right? So and then I have this as a joke, as a dichotomy. This is a quote from Chariots of Fire, right? So I believe God made me for a purpose, but he also made me fast. So the idea is that if you are fast, I choose you, right? So to work on the architecture so that it can give you 3 times better performance, or just make the architecture 10 times better faster. Which one would you put your money on, right? So it's much easier to accelerate and then get a bigger model and let's wait until converge than trying to come up with the next version of transformers, right? But it might work, but I'm not sure. But that's kind of the ideas here. So I didn't have much time to work about this, to talk about this, but that's kind of the space that I'm living since a few months. It's like, well, we have infinite data. What are the implications for that? And that's it. And finally, is just, yes, that's the philosophy. This is for the people that believe in transformers, like pre-training on data. It can outperform everything, right? So this is Socrates, of course, life unexamined is not a life worth living. But is all data good? Like, for example, if you imagine that you attack my idea, well, your simulations do not match reality, therefore you shouldn't be doing this. But well, it's actually synthetic data. Are you going to have problems in reality about predicting synthetic data? Maybe, right? So who knows? And then if you have all the data in the world that exists right now, I got that when I was working with COVID, we basically had all the time series that we wanted with COVID, but like didn't work very well. Some deep learning architectures, right? And people are mentioning this in the natural language processing space. Like people say, well, you are actually exhausting all reliable data. What are you going to do next? And the answer for that is we still have YouTube. We haven't still processed YouTube, but might not be what when you process YouTube. Are you going to get general intelligence after that? So that's kind of the idea. And then, well, do you think that real data will solve the problems? And well, what if my data is actually white noise? That happens a lot. So if you don't care about white noise, sorry, I'm not making a good final comments, but it's kind of, this is for the sake of time, but kind of the idea that if you think about, well, are simulations in it or not? Are models good or not? Or it's just data and that's it. Anyway, thank you for your attention. Apologies for the super extended talk.
No.
Thank you. So I think we will have a bit more time to chat a bit and maybe going a bit deeper into this or that aspect. So that's why I would suggest that if there are questions online from attendees online, I would take them first. So just raise your hand if you have a question to the online audience, and then I can unmute. otherwise, I would maybe just ask one question. I mean, as I said, we will discuss a bit longer, but maybe before we kind of officially close the seminar, maybe one question. So basically all the foundation models that are out there are univariate, right?
Mm-hmm.
So, and I mean, multivariate time series forecasting is super challenging, right? Because it happens quickly that the model picks up something that is not like reoccurring in the future, right? So it doesn't really help for forecasting then and so on. However, there must be a way, right, to improve forecasting in general, but just by adding more data, right? Or to adding covariates and such. So what is your take on like this topic? Like, you know, or maybe what would you say, like how challenging it is to integrate this idea of multivariate time series forecasting, and then also in regard to the foundation models?
Yeah, so thanks for the question. Yes, I'm not super sure if none of the foundation models support multivariate, but I would not put my money on the multivariate accuracy. And it's a super hard problem, as you mentioned. And so one of the ways, of course, that I see for that, solving that, is by simulating on kind of reasonable models that are multivariate. The first thing that comes to mind is these VAR models, which are vector autoregression. It's basically linear models in several variables, which are already hard. For example, if you want specific applications of specific processes, there are in ecology, physics, etc. There are some, like the predator prey, log double Dirac differential equations. It might be some space to explore, and the physicists do the forward approach, which is we have the model and the data, the parameters of a model, we can guess them or are not important. They don't recover the parameters from the data usually. Sometimes they have to do it, but it's kind of the forward. But kind of the idea is, well, can we get some mathematical description of some multivariate process that is realistic, and then pre-train on those, and we can get. I'm hopeful that this will get like good results, relatively speaking. So at least let's say that not do much worse than a multivariate and univariate when the things are hard. And also, well, another issue is that, well, start with some space, some domain where we know a multivariate model that works, and then mimic those, and then go for that instead of just, well, simulate from linear vector autoregressive and then just plug them in data. But that I would be, I'm excited to approach that. But yes, as you mentioned, it's a super hard problem. So if I don't want to get too depressed when working on that, so let's nail univariate first and then try to expand on those. Also, another reason that might be behind the multivariate is that sometimes it's very hard to, I guess circular reasoning, but it's very hard to get any other variable, to guess any other variable that might affect the process. Either you don't have it, or it's difficult to get. Of course, you can argue that, well, if you have a good model that can do variable selection, or you can throw everything like the kitchen sink approach, throw every covariate that you think might work, like the time of the day, the letter of the day that we are today on, all of those covariates, and some might work. But the idea is that there are some cases where the covariates, we don't know of many covariates that might help, right? For example, I guess COVID was a good case because we can think, well, for mortality, we have infections that will, for sure, we're going to be predictive of the mortality. We have the vaccination rate. We have, and then we could have even some explanatory variables of mobility and to see the effect of lockdowns. We have those, but very quickly we can run out of ideas. And then in other settings like, I don't know, like the sales of shampoo, then it's more difficult. For example, one variable would be the demographics in your area, but you might not have access to good quality data, or it might be like in a frequency, or it can even, like the noise in predicting the demographics of your area can be worse than the other. But yeah, so basically what I'm looking for in the multivariates is at least a multivariate model that will give you the zeros in no. Don't give this variable, does not help, right? So I would be happy if it can already learn that.
Yeah, that could be a good start, right?
And well, and maybe yes, and maybe that we have this slide of the adversarial. It can also be used in that. Well, I mentioned maybe people might be lost in not me, but I think in the multivariate, like in the adversarial, well, can I craft multivariate process that will, you know, make you work really perform really badly, and then try to learn from those?
Yeah.
And but yeah, that's the way I see it. So basically, look for the notable models, and the notable model that I know is the linear autoregressive, the VAR, and don't be disappointed by the fact that these are linear models that are they can create extremely complex patterns. And if you even add some nonlinearity, like you scale by x and x squared, you get into the chaotic time series territory, which we know that they are not possible to predict because they go beyond numerical accuracy of the machine. So that's kind of the thing. Like, it's very easy to make other arguments for nonlinearities in the time series space. So
okay, thanks a lot. Having a look at the time, I would say we have an official ending of the seminar, and then, as I said, like, people who are here can stay a bit longer to chat a bit, and yeah. So thanks again to all people who joined online. Thanks for coming, and see you at the next seminar. I can actually make an announcement. So the next one will be end of May. It's May 29, and the speaker will be from Italy, and she will join online. So it will be in the evening. So it will be a Wednesday evening at 6 p.m. And yeah, I will send around invites soon. So have a nice day and see you around.